Excellent. So our next speaker is Igor Pikovski, who will be speaking on a quantum optics approach to testing the gravity-quantum interface. Take it away, Igor.
Yes, thank you. Thanks a lot. So I apologize, I was not able to be there in person, but I appreciate the opportunity to connect this way. I first want to really thank Rick for organizing this really wonderful RQI circuit. I'm enjoying it very much, and will also follow up on some of the talks that I had to miss so far, as well as, of course, thanks a lot to Jermaine, Vasilis, and Eben for making it possible in Stockholm. So the PIs were asked to give a little bit of an overview of the research in the field. So the next 20 minutes or so will be my attempt to give an overview of the type of research we are currently interested in and the different directions that we're pursuing. So in summary, this is, in some sense, a quantum optics theory approach to understanding and testing the interface between quantum theory and gravity. And I will try to guide you through some of the directions in the next 20 minutes or so. So first, kind of a summary of our group is we are interested in the interface at low energies between quantum physics and gravity. And in some sense, I would call it non-relativistic RQI. In the sense that the tools we use are non-relativistic quantum theory and quantum information approach. And that combined with effects of gravity and fundamental questions about general relativity interfacing quantum mechanics. And sorry, I just have to ask, I heard a little bit, is everything all right? I'm not sure if you were trying to tell me something about
Yes, everything's working, Igor.
Okay, perfect. All right, great. So what does it mean to have a quantum optics information perspective? Kind of what are the type of research questions we're asking? One is, for example, how does gravity affect quantum phenomena that we're all familiar with at low energy theory? And what novel effects may arise? So can we test also some aspects of the quantum nature of gravity and whatever such a test would even mean, and what we can learn from that? Then finally, what can specific experiments with atomic, molecular, and optical systems, even in principle, reveal about this interface of quantum theory and gravity? And of course, there's a natural question, why do such experiments with AMO systems or tabletop experiments in general, what role can they play? And that, of course, has been addressed in some form in previous RQI talks as well. And one big motivation for that is that there's a lot of experiments in the recent decades that are really pushing quantum optics or quantum control of quantum systems into entirely new domains. One example is the development of atomic clocks, atomic technology, where over decades there's been here even increasingly exponentially and even more exponentially improvement in terms of precision of measuring certain phenomena, in this case, precision of frequency. Other systems that are being developed are also atomic systems, but that can be delocalized over very large spatial superpositions, such as in the Kasevich group, Müller groups, and so forth. And other examples of systems are optomechanical systems, where you really push quantum physics into entirely new mass scales, and that can range from picogram all the way up to kilogram devices, where we can study and probe quantum phenomena. And so a natural question arises here: if one has these new capabilities in different scales, what type of novel questions about the foundations of physics, and in particular about gravity, one can ask and explore? So that is really the main core interest of our research group. And the next slide is an attempt of mine to kind of try and summarize some of these different directions on one slide. So we do focus on a quantum optics and quantum information approach from a theory perspective. And there's different questions that one can ask. One is just in general, not related to gravity per se, is the quantum control of novel quantum systems. So the question of what kind of quantum phenomena can we explore in entirely new systems, what new capabilities do such systems provide, and how can we test quantum physics in these entirely new scales? And this could be something like atomic metasurfaces, optomechanical systems, atomic clocks, and so forth. A related question is, how can we use such systems in order to gain some inherently quantum mechanical advantage? and in particular, what kind of directions do these systems provide in quantum sensing. And so this is an exploration of basically quantum advantages of systems closely related to the foundations of quantum mechanics, what it is exactly that provides us an advantage. And then one can apply these type of devices and maybe novel approaches to high precision experiments. And so ask questions about what novel aspects of general relativity or maybe alternative routes to test general relativity could you provide, such as, for example, novel type of superfluid helium resonators or atomic clocks in space. And here, this example is exploring how they can be used for gravitational wave detections complementarily and in different ways to standard approaches. Now, another different aspect of using quantum optics is more from a theory side, and kind of a low energy perspective on phenomena which are usually studied in different domains. And so another example is what we look at is, for example, phenomena in cosmology or beyond standard model physics, such as dark energy or dark matter, and studying how some of these known phenomena from quantum information science, what they can reveal about our understanding of these kind of fundamental models. And so here's an example where we studied, for example, squeezing in dark matter axion models. And then kind of a large aspect of our research is studying so-called tabletop quantum gravity phenomenology. Namely, if there are some tests of some models, speculative models of quantum gravity that we can perform with some of these novel systems, and what type of input, experimental input there can be for the expected or maybe speculative behavior due to the interface of quantum mechanics and gravity. In general, focusing more on known physics, one can also ask questions about how does general relativity change some of the quantum phenomena that we know and that we can explore. So what type of general relativistic features can one actually probe within quantum theory, where GR might not necessarily be quantized, but can still have an effect on quantum mechanical probe systems. And then closely related are, of course, the questions about what indirect tests of quantum gravity can one make, what can one deduce from such experiments, and in general, what type of discussions can one have or motivations that shine light on different phenomena and different concepts that underlie gravity and quantum theory. So what can one learn from something like the Duncan experiments about it as well? So here is, for example, a drawing from George Gamow from 100 years ago, where he drew Bohr and Landau very fiercely debating about the need or lack thereof of quantization of the electromagnetic field in similar spirit back then. And then finally, I want to mention the newest result from our group, where we show and analyze that it is actually possible also to combine these questions about indirect tests of quantum gravity and gravitational wave detection in order to see some signatures of single gravitons as we expected. And I'll say a few words about this later on, but there will be a dedicated talk to that by Germain later in the afternoon. Okay, and now quickly flashing also all the people that actually do the majority of the work. So we have, often also masters and we have bachelor projects, but I do want to highlight that we do have upcoming open PhD and postdoc positions, especially for this RQI crowd. So if there is any interest, please feel free to reach out. You can just email me directly if you're interested. So in summary, we focus on quantum optics theory, gravity, and the foundations of quantum mechanics, as well as gravity. Okay, so now a little bit more concretely, to give a few examples of some of the research directions that we are pursuing. In many ways, to understand how one can ask specific questions using this quantum foundations approach is to ask very fundamental questions about both theories. So the foundations of quantum theory and gravity are very different, and they're built on very different fundamental principles that we assume to be valid. So on the quantum mechanical side, it's inherently probabilistic. There's no commutativity. It has a unitary linear evolution. On the gravitational side, it's completely different fundamental principles, such as the equivalence principle, space-time geometry, and then the fact that space-time itself is a dynamical quantity. Now, from these fundamental principles, of course, there's many more, and one can structure in different ways. But in principle, there are these different foundations, and they also result in different phenomenology. So some observable consequences on the quantum side are something like wave-particle duality, so interference of particles, really, entanglement, uncertainty relation, Bell inequality violation, and also, of course, high-energy phenomena, such as particle creation, fluctuations, and so forth. And on the gravity side, well, to lowest order, we have just the regular Newtonian force, but we have, of course, post-Newtonian corrections, but they're not just a correction to the force, but there's a metric nature to that, showing itself in unique phenomena that don't appear in other theories, such as time dilation. We also have predictions, strong field predictions, such as black holes, and resulting phenomena like gravitational waves, and, and very funky things like closed time-like curves, and so forth. So, of course, it's not an exhaustive list, but just to give a little bit of a flavor. And so one approach in this kind of in some sense, the mindset that we often pursue is, well, when and where do some of these different concepts of phenomena intertwine? And can we shine light on this? And in fact, some of these, of course, have been experimentally tested already and have been seen. And the most famous example is the interplay of the wave-particle duality or interference of matter waves in the presence of a Newtonian force. And this goes back to Colella-Oberhauser-Werner some 50 years ago or more. And this is exploited since then in many other setups, such as atomic fountains, the Kasevich group, Müller, Tino, and so forth. There's many, many groups working on that, also just for technology development. So this is a regime that we understand well, and that we have exact experimental input where there's no speculation needed about whether things work together or not. And so just kind of as a very brief summary of this aspect is basically we know that we can add the Newtonian gravitational potential into the quantum evolution of systems. And so if we have a matter wave that's delocalized in the Earth's gravitational field, well, it will experience a phase shift due to the Earth's gravitational field. And this phase shift is proportional to the separation of your wave packet, as well as the time. And the key of that is, even though it's a gravitational phenomenon, it's divided by h bar. So it's actually very large and visible phenomena, which is what Colella-Oberhauser and Werner realized. And you can see this phase shift in simple experiments, such as, for example, cold neutrons here in a Barak diffractor, where you create this type of interference pattern, and it's on centimeter scale. So you just rotate it, and then you can scan this gravitationally induced phase shift. And as I mentioned, that's, of course, the same fundamental principle behind atomic fountains. So what we learn from such already performed experiments is that, well, we can add gravity in the same way as we add other interactions into our description of quantum systems as an external potential. And it does change something uniquely quantum mechanical. It coherently induces a phase shift, which is given by the Newtonian gravitational field, or one can extend it even to the tidal forces and so forth, which has been recently done. What we don't learn from such experiments are two unique questions that arise when we have gravity. One is, well, gravity is a metric theory, and so going beyond the Newtonian limit is interesting because we do want to probe something that's unique to general relativity. It does not have an analog in other interactions. And the other question, of course, is what about the quantization of gravity itself? So if we have to include that in our experiments, we would be, then testing really quantum gravity. And in many ways, what we do, as well as the broader field, of course, does it with many, many groups that also talked here at RQI and others, is exploring these two different directions in different views. So modifications that allows either or both to study some kind of GR corrections and or study the questions about the quantization of the gravitational degrees of freedom themselves. And there's different ideas and many, many more maybe unexplored ideas how we can go into these directions. It's a very exciting field to work in and kind of still, I think, in a very, very early phase. And so let me give you just an example, a few examples, in fact. I'll briefly run through that in the next 10 minutes or so. One is, well, there is another interface we can look at. So going beyond the Newtonian force, we can look at post-Newtonian effects, and in particular time dilation, which is unique to GR, and see how that intertwines with this matter wave interferometry. And that is really something that we work with together with Magdalena Züch, Fabio Costa, and Czeslaw Bruckner when we were back in Vienna working together. Now Magdalena and Fabio both are in Stockholm as well with their own research groups, and still, of course, exploring these directions, because it turned out to be a very rich and very promising new field where there's a lot of interesting questions to be asked. So I just want to very briefly summarize that. And of course, we spoke long ago at RQI about these things as well. So in principle, what this amounts to is a quantum twin paradox type setup. So what it means is that instead of just using matter wave interferometry as in the usual cow experiment, we also use additional degrees of freedom which can also measure time. And then we put them in superposition as well. And so putting that in a gravitational field really shows entirely novel phenomena. And in particular, there's new effects that arise because gravity now couples to both external and internal degrees of freedom, if and only if you include post-Newtonian corrections. And there's new quantum effects. Well, what are these quantum effects? And they really just go back to this fundamental principle of Bohr's quantum complementarity, which is summarized here in these two pictures. Namely, there's interference if you don't look at it. If you look at it, the interference washes away. Okay, so there's a trade-off between visibility and distinguishability in quantum mechanics, which I just want to briefly flash. And that is really what's happening here in this kind of proper time interferometry that we proposed, or clock interference, or single twin quantum twin paradox, or something like that. And the main point is that, well, so far experiments either do these interference experiments with matter waves, or they take atomic clocks and they measure them very precisely time dilation, but it's very well defined world lengths. And so if you have two atomic clocks, for example, and they measure some kind of time dilation, which they do now even on millimeter scales, well, they really probe that the time evolves with these clocks with respect to different proper times. And according to the linearity of quantum mechanics, you can also take a single clock, put it in superposition, and then it will experience the superposition of different proper times. And that's kind of the key aspect that we shine light on, that this is a new type of test of the interplay of GR and quantum mechanics. And due to quantum complementarity, there is a very unique signature of that, namely that there's because of this different time dilations experienced by the same clock, there will be an effect that washes out the interference. And it's summarized here. So I'm rushing a little bit because I think I was told I have only 5 minutes left. So just to give you a little flair, there's an older work. So in principle, you can see this interface of quantum theory with post-Newtonian corrections, and there's new effects that arise, such as the modulation of your interference pattern. And you can extend it to many different domains. The periodic clocks, you can look at actually picture of clocks, which causes decoherence. You can look at photonic versions of that, where you can study different aspects of the period delay, and so forth. And then what we're recently studying with my collaborators is we're looking also at quantum networks of clocks and how such similar effects arise there as well, which we hope to finalize hopefully in the next few weeks. Okay, and then shifting gears now, well, there's other different proposals. This is what I talked about now, was going in the direction of adding general relativity to the mix. Well, can we also add something about the quantum nature of the gravitational field to the mix as well? And these are very famous and popular proposals that have been done in other groups, namely by Sugato Bose, Latko Vedral, and collaborators, Perche Kim, Jerry Milburn, and so forth, where they explored the what we can learn about the quantum nature of gravity when we interact between two systems that both source the gravitational field in superposition. And it's a very interesting proposal. Basically, it's two cow experiments next to each other, and they interact gravitationally, and that induces entanglement. And so I just, I think I'm, let me see. Oh yeah, I don't have much time. So I'll just very briefly rush through that because this has been, of course, discussed in many different fields. Our goal here was to analyze what it is that one can learn from such experiments. So one really generates entanglement. And the question is, this is an indirect test. So how is this entanglement generated? And what can we learn about the underlying nature of gravity depending on our different assumptions. And so, just to mention briefly, this is what we analyzed. This is what we analyzed in this paper here more recently. Basically, trying to give clarity because there's debates, and all the debates stem, in fact, around the fact what fundamental principles we take for granted and what we deduce. And so, all of these different answers are kind of mutually correct, depending on what starting point there is. And so, in short, it is quite ambiguous about what we learn about it, depending on what we elevate as some kind of the ontology of how entanglement is generated. So you can look more here in this research paper. So what it basically shows that in the Newtonian case, it's clear we generate entanglement, and that's actually a similar test of kind of the new quantization of Newtonian potential as CMB observations that we already have. And if you take relativity as a starting point, well, there's a local and a non-local description. And in the local one, we learn about the quantization of the mediators, but of the mediators, then we have to elevate ghost particles, such as spin 0, spin 1 gravitons, that we usually don't assume can be observable, but they are the ones that mediate entanglement. Where in the non-local case, one can also generate entanglement non-locally. And so it all depends a little bit about what one can learn from these experiments. Maybe one has to modify this setup somewhat to distinguish these different interpretations. Okay, and then finally, just in the last minute, I just want to say our newest work, which Jermaine will talk much more about, is we studied something completely different. We asked the question if it is possible to detect single gravitons as we expect them directly, real ones. And this is the interface of gravitational waves that we know in the wave-particle duality, namely the discretization of waves. And so this is a paper that just appeared a few months ago on the archive, and you can look at it here. And just as a one slide summary, it is possible to detect single gravitons. And the key ingredients for that, which we outlined, are the following. One has to focus on macroscopic quantum systems as your detector. One has to focus on stimulated emission and absorption of single gravitons. One has to focus on quantum sensing, in particular of quantum jumps, and one has to correlate the results to independent classical detections that can tell us what source it is that is inducing that. And with all this, it is possible to detect single gravitons even in realistic experiments. And that's what we outlined, and Jermaine will tell you much more about in just a little bit. And the upshot of that is, well, there was a debate, and in fact, there is an expectation, has been for decades, that gravitons are not detectable, that there's no way to do that in realistic experiments. Famous example is Dyson's paper here recently. Well, we show that that's wrong. It is possible to do it. And instead, what is the correct way to do that is a combination of basically Einstein's insight about the photoelectric effect and how that teaches us something about the quantization of the radiation, combined with kind of detectors which operate in a quantum regime, but are based not on LIGO, but are based on this kind of bar detector technology. Okay, and with that, I'll just skip this since I think Evan wants me to finish. So this will be in much more detail discussed by Jermaine, and I hope you tune in. And so with that, I just want to summarize. There's a few examples I wanted to give. There's many more. And in principle, we explore this interface of using quantum optics and control, and then applying that to very fundamental research questions related to the foundations of gravity and quantum theory. Okay, and with that, thank you for all your attention, and especially, of course, thank you for all the group members for making it all possible. Thank you.
Excellent. Excellent. Thank you, Igor. I think we've got time for one question. Do we have anything? Yeah.
Igor?
Yes. Hi. Yes.
Hi.
Hello, Favar.
Hello. So what was the statement about the spin 0 and spin 1 components of gravity with producing entanglement?
Sure, just 1 second. I'll reshare. Yes, I rushed through that, and I apologize. The statement is the following. So how the core statement to learn something from these experiments is to understand how is entanglement generated. So we have systems that source gravity. We don't probe gravity. And then the question is, well, how does gravity create entanglement? And there's different pictures, which are all they're all correct. None of them is more correct than the other. It's just a choice of how we think about it. And all of them describe the same physics. And there's a local picture one can impose to say that, well, there's an exchange of particles that create entanglement. And one can show that in this particular case, for this type of setup, the dominant interaction that creates this entanglement involves only degrees of freedom in this local picture, which are not the real gravitons, so not spin 2 gravitons, but the kind of scalar and vector degrees of freedom. And this is because in this local picture, one has actually 10 degrees of freedom that one later just puts, by constraints to not to be unobservable. So instead of 2 degrees of freedom, there's 10. So this is the Bloyer-Gupta quantization procedure. But in virtual processes, such as the creation of entanglement, they can play a role. And it's in fact them that directly create entanglement. So one can use the local picture to think about it, that there's something that has to be quantized, but what one has to quantize are then spin 0 gravitons or spin 1. So like these ghost particles have to be quantized in this picture. Is that clear enough, or was it a bit too?
Yes, no. This is because this is of course completely expected also, because even for electromagnetism, the Coulomb field of electrostatics is not a propagating photon. It is the It is longitudinal and combination of the field components that are not physical, basically as propagating modes. And
exactly. And here it's exactly the same, except for now one has to elevate them to physical quantities because one wants to say that entanglement is generated locally.
Yeah. So they are of course always physical, but they are not freely propagating.
Right, they're not freely propagating or individually observable.
Yeah.
But for entanglement generation, in the local picture, they are the ones that matter.
Yes.
In the non-local picture, they don't matter. So
Yeah.
it all depends on what basically in fundamental assumptions one takes. That's why they define what conclusions you want to draw from such experiments.
So Newtonian gravity is in fact mediated by the scalar mode, which is not a propagating mode. And it's perfectly physical, of course. It's a force. Thanks.
Well,
that's clarifies.
Exactly. I only would just caution what it means by physical, because that's in the eye of the beholder. Somehow, that's our point. That we want to be just very, very agnostic. Just to say, look, if this is your assumption, that's what happens. If you think something else is maybe more physical, then you have a different interpretation of the experiment.
Okay, I agree. Thank you.
Excellent. Let's thank Igor once again.